Good morning, students. Today we are going to start the new group of P block element, that is group 17, known as halogens. Students, you must be knowing that why the group 17 is known as halogen and what is the position of the group 17 in the periodic table. Okay, now let's see the position of the halogens in the groups in the periodic table at first. The elements in the group 17 of the periodic table are on the right side, right, with the first member being fluorine, second chlorine, bromine, iodine and astatine, right? So the first member of the group is fluorine and the last member of the group is the astatine. Students, when we will discuss the general characteristics of the group 17, we will discuss till iodine, as the astatine is the radioactive element. Now students, a question generally comes in our mind that why the group 17 members are known as halogen. So why the name halogen? So students, halogen metal compounds are salt occurring in seawater. Halo means salt and gen means producing. So the salt produced in seawater, generally sodium chloride, right, fluorides, chlorides, iodides, even the bromides, these are the salts which will be found in the seawater, and that's why this name has come. Now students, the salts of halogens, fluorine state, this is a state of halogens. So fluorine, its color is yellow, chlorine it's green. Okay students, one thing more, that the state of halogen, it is not found in the nature in the monoatomic state. It will be found in the diatomic state. So fluorine, chlorine, bromine and iodine, these exist as a diatomic molecule. Color of fluorine is yellow, right? At room temperature and pressure, normal pressure, it will be at gaseous state. Chlorine will be also at gaseous state. Bromine is red brown colored liquid, and students, iodine is a gray color solid. Now if we see there's a vapor color, so fluorine will be yellow vapors, chlorine green, bromine reddish brown, reddish or brown, and iodine purple. Student, astatine will exist in the form of AT only, and it is a radioactive and is one of the rarest of the chemical elements. Now students, we are just go through the Greek name of the fluorine. Fluorine has come from the word fluore, Greek word which means flow. Chlorine is chlorus, which means color greenish yellow. Bromine is bromose, which is tinge. Iodine, iodes, violet. Astatine, astatus, unstable decay product of uranium and thorium. Right, so astatine is a radioactive, so that's why it's unstable, and it's a decay product of the uranium and thorium. Now students, we will discuss the general characteristics of group 17 elements, right? So general properties of the halogen, that is, they all in common have 7 electrons in their outermost shell. They exist as a separate diatomic molecule, fluorine, chlorine, bromine, BF2Cl2Br2, colored, and our color darkens as we go down the group. They all are non-metals. They do not conduct the electricity. They are never found in free state in nature because of their reactivity. They will be found as a compounds with the metals like NaCl. These are poisonous and smelly. They are all toxic or harmful because they are very reactive. Now students, we just have a look on the electronic configuration of the halogens. Fluorine you know its atomic number is, students, how much? It's 9. So configuration will be 1s2, 2s2, 2p5. Chlorine atomic number is how much? 17. So we will write down the condensed electronic configuration: neon, then 10, then 3s2, 3p5. Bromine, it's argon 18, then we will write 3d10, 4s2, 4p5. So students, similarly you will write down for iodine and astatine, right? And what you will find in common here, that is they have the outermost shell electronic configuration as ns2np5, right? So whether it be 2s2 2p5, 3s2 3p5, 4s2 4p5, 5s2 5p5, and 6s2 6p5. Yes, students, the electronic structure of halogens. All halogens have got 7 electrons in the outermost shell, but 1 electron short of to gain the nearest noble gas configuration. And this they can easily attain by gaining 1 electron. They all gain an electron in the reactions to form a negative ion and gain a negative charge. So they all have these similar chemical properties. Fluorine is the most electronegative element in the periodic table, and it has got no d orbitals in its valence shell, so it cannot expand its valence shell. Chlorine, bromine, iodine, they all have the valence shell d orbitals and can expand their valence shell to hold as many as 14 valence electrons, right? So you can see the electron dot structures of the fluorine, chlorine, and bromine. Now, how do the halogens molecule exist? So as I said earlier, they exist in the diatomic state. All the halogens have atoms requires 1 electron to gain the stability. Each atom can achieve this by sharing 1 electron with another atom to form a single covalent bond. Hence, the halogens exist as a diatomic molecule: F2, Cl2, Br2, and I2. Now, the melting and boiling point of the halogens increases down the group as the molecule becomes bigger. So, you can see here the relative size. The fluorine molecule is smallest, and the iodine is having the maximum size, right? And if you see the melting point, right, it also increases as we move down the group, and boiling point too increases as we move down the group, right? So the force existing between the molecules is weak van der Waals forces, which increases down the group due to increase in the molecular size. As a result, the melting and boiling point also increases. Now students, the physical properties of halogens which show a regular gradation, right? After group 1 and group 2, it's group 17, right, which will show a regular gradation in the properties of it. So first property is the ionization enthalpy, electron gain enthalpy, electronegativity, oxidizing state, oxidizing power, electropositive nature, right, and the atomic and the ionic radii. It's not mentioned here, but we will discuss this also, atomic and ionic radii. Now students, halogens have the smallest atomic radii in their respective period, and this is because of the maximum effective nuclear charge. If we compare the group members, the fluorine is smallest in size, right, and the size increases as we will move down the group. The students, the radius of the halide ion, if we compare fluorine with F negative, the F negative will be greater in size than the corresponding halogen atom. And we have gone through it in class 11th also, that the size of the anion is bigger than the parent atom. And why is it so, students? Because the effective nuclear charge right, it is going to decrease, right, in case of halide ion. Per electron is reduced and the electron cloud is held less tightly to the nucleus. This causes the increase in size. Okay, now we will discuss ionization enthalpy. Now, ionization enthalpy of halogens is very high, and this indicates, students, that it has got very least tendency to lose the electron. However, when we move down the group from fluorine to iodine, the ionization enthalpy decreases, and this is due to the gradual increase in the atomic size, which is maximum for the iodine. Hence, the least ionization enthalpy in the family will be of iodine. Now, next is the electron gain enthalpy. All these have maximum negative electron gain enthalpy. Why? Because they have strong tendency to accept one electron to gain the stable noble gas configuration, that is Ns2np6. In general, electron gain enthalpy become less negative as we move from top to bottom, that is from fluorine to iodine. So accordingly, fluorine will be having the highest negative electron gain enthalpy, but it has been found that chlorine has the highest negative electron gain enthalpy in the group. And this is because fluorine is having the smaller size. As a result, there is a strong interelectronic repulsion in the relatively small 2p subshell of fluorine, and thus the incoming electron doesn't get the much attraction. Hence, students, the negative electron gain enthalpy, right, students, of the halogens varies accordingly. Fluorine will have the lowest, right. Fluorine has got the least, chlorine is having greater than chlorine, right, then bromine will be less, and then finally iodine, right, students. So just have a look on the written facts which I have discussed orally now, that the ionization enthalpy defined as you know that it's defined as the amount of energy required to remove the most loosely valence electron of an isolated gaseous atom to form a cation. Now, if the outermost valence electrons are far away from the nucleus, it doesn't take as much energy to remove them, so the energy required to pull off the outermost electron will be less for the elements at the bottom of the group, since there are more energy level. So iodine loses an electron and forms I positives, right, students? So as we will move down the group, students, due to increase in size, the magnitude of ionization enthalpy is going to decrease. So the high ionization enthalpy makes the element appear non-metallic. Iodine and astatine display the metallic property, right? So ionization enthalpy decreases down the group. Now, students, we will discuss the electronegativity. Now, the halogens have electronegativity. You know, it's a measure of tendency of an atom to attract the shared pair of electron toward itself. So the valence electron will be at distance from the nucleus as we go down the group, and therefore the nucleus and the electrons are not much attracted to each other. An increase in the shielding is observed. So the electronegativity decreases down the group, right? So because of smaller atomic size and greater effective nuclear charge, fluorine is the most electronegative element in the periodic table, right? Now we have discussed the electron affinity or the electron gain enthalpy, right, students? Now next is the oxidizing state of halogens. We have discussed, students, color also, right? That the fluorine is light yellow in color, chlorine greenish yellow, bromine is reddish brown, and iodine is dark violet. Now students, we will discuss the oxidation states of halogens. Halogens have only one electron less to gain the next noble gas configuration. Therefore, they generally show the -1 or +1 oxidation state. Since fluorine is the most electronegative element, it will always show an oxidation state of -1. It doesn't show any positive oxidation state. So students, among the halogen, it's fluorine which show only -1 oxidation state. It doesn't show any other oxidation state. Whereas other members, chlorine will show negative as well as positive oxidation state, right? So the other elements show the positive oxidation state of +1, +3, +5 and +7. The higher oxidation state of chlorine, bromine and iodine is due to the presence of the vacant d orbitals in their valence shell. As a result, the outer s or p electrons can easily be jumped to the vacant d orbitals, right, and show the higher oxidation state. These higher oxidation states are realized mainly when the halogens are in combination with small and highly electronegative fluorine and oxygen atoms, right, in oxides, oxoacids and interhalogen compounds. The oxidation state of +4 and +6 occurs in oxides and oxoacids of chlorine. So students, you can see that except fluorine, other members are showing the positive oxidation state, and that too higher oxidation state. -1 is the common oxidation state shown by the halogens. Now students, the oxidizing power. It decreases down the group. The halogens are the strong oxidizing agent, and the oxidizing power decreases from fluorine to iodine. Fluorine is the strongest oxidizing agent. It oxidizes other halide ions to halogens in solution or when they are dry. So fluorine plus 2x negative. So students, here x can be either chlorine, bromine or iodine, right? So it will get changed to F negative, and that halide ion will get changed into diatomic state. So that is, fluorine has got high electron gain enthalpy here. Halogens of low atomic number oxidizes the halide ion of higher atomic number. So the one which is having a lower atomic number will oxidize the halide ion of the higher atomic number. Now students, here it is pictorially represented as we have got Cl2 aqueous chlorine and 2I negative aqueous iodine. So Cl2 is having the lower atomic number, so it will act as a stronger oxidizing agent, and it will oxidize the iodide ion which has got greater atomic number or higher atomic number than chlorine to I2. Cl2 will therefore displace iodide ion from solution, and I2 will not be able to displace chloride ion, right? So the solution results in the pinkish color in the carbon tetrachloride solution. Now, how does the electron structure affect the reactivity? The reactivity of alkali metal decreases down the group. So the atom of each element get larger down the group, right? This means the outer shell gets farther away from the nucleus and is shielded by more electron shell. Farther the outermost shell from the attraction of the nucleus, it will become more difficult. So we can say that it will become easier to get that electron removed from the outer shell easily, and this is why the reactivity of the halogen decreases down the group as the attraction for the incoming electron will also decrease. So fluorine, chlorine and bromine and iodine, the reactivity decreases down the group. Now students, the fluorine is the first member of the group. So like other groups, the first member always show the anomalous behavior. Its anomalous behavior is because of its smaller size, higher electronegativity and non-availability of d orbitals in fluorine. Now what are the peculiarity or abnormalities shown by the fluorine? The first one is oxidation state. All the members except the halogens show the negative as well as positive oxidation state, whereas fluorine only show the -1 oxidation state. Reactivity, fluorine is the most reactive element among the halogens, and this is because of strong electrostatic repulsion between the non-bonding electrons present in fluorine molecule. The FF bond is very weak. Behavior of hydrogen fluoride. HF has abnormally high melting point and boiling point because of strong association, which is because of the hydrogen bonding, which has not been observed in HCl or HBr or HI. Formation of HF2 negative ions. Due to hydrogen bonding, students, the fluoride ion forms the anion HF2 negative. On the other hand, other halides do not form such ion. Right? Example is KHF2. Maximum covalency. As fluorine lacks d orbitals, it cannot have covalency more than 1, but the other members can have covalency up to 7. Formation of SFs due to its smaller size and high electronegativity. Fluorine brings about the +6 state in sulfur, right, forming SF6. Other halogens do not form hexahalides. It undergoes the complex formation also, and it also forms the polyhalide ions. Good morning, students. Today we will discuss about the interhalogen compounds. Now students, what are these compounds? These are the covalent compounds which are formed when two different halogen react. Yes students, the two different halogen atoms will react with one another. These are formed due to the electronegativity difference among the halogens. You know that the halogens are electronegative elements, but then also there is a difference between all the halogens in terms of electronegativity. Interhalogen compounds have a general formula AXN, or you can also write as XX dash, where N stands for 1, 3, 5 and 7, and you can easily relate it with the oxidation state shown by the halogens +1, +3, +5 and +7. Interhalogen compounds are classified into three types: AX, AX3, AX5 mainly, and AX7 also. AX type. Here students, what is A and what is X? Right? So A is the less electronegative halogen. The element which will have less electronegativity, or we can say which is more electropositive, will be written at first. So AX, A is less electronegative than X. So if we take example ClF, so Cl is less electronegative than fluorine. Similarly, we have BrF5, BrCl, ICl and IBr. So next type is AX3 type. A here again is a less electronegative element, and X is the more electronegative element. And since here the oxidation state shown by the less electronegative element is +3, that's why it is ClF3, BrF3 and ICl3. In the similar way, we have AX5 and AX7. Now let's take the first example here, iodine monochloride. It's ICl. It is formed by by passing the chlorine over solid iodine at a temperature below 0 degree Celsius. So it is I2 plus Cl2 gives 2ICl. So here you can see that the molecule ICl is represented by the two circles where I is larger in size and Cl is the smaller in size. This compound is red-brown chemical compound and it melts near room temperature. Because of difference in the electronegativity of iodine and chlorine, ICl is highly polar, I plus and Cl negative. In organic synthesis, estimation of iodine number of oils and as a source of I plus, iodine chloride is used. Next student is bromine trifluoride Brf3. It is obtained by mixing the bromine vapors and fluorine in a stream of nitrogen at 20 degrees Celsius. So nitrogen provides the inert atmosphere. It is a straw colored liquid with a pungent odor. It's a powerful fluorinating agent. It is used to produce uranium hexafluoride in the processing and reprocessing of nuclear fuel. So in Brf3, student, which atom will be bigger in size? Br, right? It is shown by the red one and the green one is showing the F3 fluorine atom. Next student is bromine pentafluoride Brf5. It is a pale yellow liquid and by the direct reaction of bromine with excess of fluorine at a temperature over 150 degrees Celsius, bromine pentafluoride is obtained. It is an extremely effective fluorinating agent, converting most uranium compounds to hexafluoride at room temperature like Brf3. Student, here Br is bigger in size and it is less electronegative than fluorine atom, and the 5 fluorine atom are surrounding the Br atom. Now student, next compound is iodine heptafluoride. Students, we are discussing an example from all the type of interhalogen compound. Now we are taking the example from AX7. It is a colorless gas. It is prepared by passing a mixture of iodine pentafluoride vapors and fluorine through platinum tube at 300 degrees Celsius. IF5 plus F2 gives IF7. So at the center, students, will have iodine, which is bigger in size, and 7 fluorine atoms are surrounding it. It's a strong oxidizing agent and it is used to prepare periodic acid. Students, generally all the interhalogen compounds, they are the covalent and are diamagnetic in nature. In general, interhalogen compounds are more reactive than halogen except fluorine, because the AX bond in interhalogen is weaker than X-X, that is the bond between two halogen atoms, except in case of F-F. You know that F-F has got low bond dissociation enthalpy. All these interhalogen compounds undergo the hydrolysis. Now students, just have a look on the shape of the interhalogen compound, because generally we get the questions related to the shape also, that you have to draw the shape of CLF, CLF3, BRF5 or IF7. CLF is linear shape, right? CLF3 of the type XY3 is T shape. XY5 type is BRF5 and it is square pyramidal in shape, and XY7 IF7 is an example of it, which is pentagonal bipyramidal, right? So at the end we can conclude that in the interhalogen compounds, the first element which we will write, it will be less electronegative, right? And it will be of larger in size, right? So here the less electronegative element will be larger in size, and the which one is more electronegative will be smaller in size. Please do underline this point, that the electronegative element, the less electronegative element will be larger in size and the more electronegative element will be smaller in size. Right? These are the covalent compounds and are diamagnetic in nature, which you have to keep in mind. Student, the uses, though we have discussed a few uses, now interhalogen compounds, they can be used as a non-aqueous solvent. They are useful fluorinating agent. That means they get the other substance fluorinated, like ClF3, BrF3 are used for the production of UF6, uranium hexafluoride, in the enrichment of uranium-235. Right, students? So just go through it and get it noted down.